approve? What? Okay. Another rip?
All right. Thanks. Hi, my name's Peter Grehan. I'm one of the authors of bhyve, along with Neil, who couldn't make it to Tokyo this time. I'm going to talk about how bhyve started and also what we're kind of looking at doing next. I won't talk too much about the state now. I think Takuya covered that very well. So if we just go back to 2010, there are a number of proprietary hypervisors around. I think everybody knows at least VMware, but Parallels is another one. There were certainly quite a few. I think at that stage it was still considered worthwhile intellectual property. There were at least 2 GPL licensed hypervisors, so KVM and Zen. But there weren't any BSD licensed hypervisors. Now, there may have been ones that we didn't know about, possibly research ones, but certainly there weren't any well-known ones. Now, the whole reason we all work on FreeBSD is basically license related, because the license allows you to use it in commercial products. So one of the big pieces missing was a virtualization story for FreeBSD. In 2010, I was working at NetApp. There was a conference in California called Meet BSD. So I did a short presentation there, which basically described some things that NetApp would like to see in FreeBSD that weren't there. I actually spent most of my time talking about PCI, I think. But right at the end, I had a slide which was basically asking the question, is anybody working on a Type 2 hypervisor for FreeBSD? And of course, no one was. So in the usual open source thing, when you have a need to do something, that's usually the way things get done. So since I sort of had a need in my workplace to at least have the option of having a BSD licensed hypervisor, and that I knew no one else was working on it, it seemed like it was a good idea to work out if it was possible to actually do one. So with Neil, we've both actually done a lot of work in low-level FreeBSD on 386 and AMD 64. I think we felt very comfortable with that part of the FreeBSD kernel. We also knew that the KVM hypervisor was done with quite a small development team. It wasn't like 50 people funded by somebody. It was just a small handful of people. I mean, they did kind of use QEMU as the basis to implement the hypervisor, which saved them a lot of time. But then again, they had to use the first version of ETX, which, as Takuya mentioned, has a lot of issues with shadow paging that does require a lot of work. But given that there was only 2 of us, and based on these things, we actually thought it might be worth a try to see if we could do one. The other thing in our favor was just around that time, Intel had kind of just moved away from the front-side bus architecture and introduced the new CPU architecture. The first generation of that was called Nehalem. So what they did with that was they introduced the nested paging into the VTX feature. So what that did was actually take away maybe 10,000 lines of code that's needed to write a hypervisor. So this also kind of put the weight in favor of a small team working on this. It turns out VTX is actually a fairly rapidly moving target. The model after Nehalem, which was Westmere, was the first one to introduce 16-bit support. In Nehalem, basically you only had native processor support. So if you wanted to run 16-bit code, you actually had to run it in an emulator or kind of use the older style virtual 8086 mode, which is sort of difficult to use. What we didn't know at the time was that that Westmere is a high-end server. So we didn't know if Intel was going to keep those features in their high-end server range. But what happened was with Sandy Bridge, they made the entire feature set of VTX available across the entire product line, and that has pretty much continued to today. So when you get a Haswell CPU, you pretty much have the same features as the server Haswell. So it just meant virtualization was available for everybody, from laptop users to people with 64 CPU servers. The other thing, because we had a small team, was rather than try to implement something that was extremely generic, we implemented something that was very targeted to our employer. So what we did initially was we limited the hypervisor to pretty much just a logical partitioning of a system. So instead of being able to run kind of any guest operating system and as many as you wanted, we limited it to a very small number, sometimes just one. We used a static memory assignment where you stole memory from the system at boot time rather than dynamically assigning it. We implemented a paravirtualized console, so during bring up we didn't have to worry about the complexity of a device model. It's just you write this byte to this I/O port that ends up on the console, and we used poll mode for receive. We didn't even have an interrupt-driven console. We just had a timer that would see if there was a character available. We also wanted to avoid having to implement instruction emulation. So with device models, Intel really doesn't give you any assist for that. You just get a page fault, and then you have to emulate the instruction that caused the page fault. And if anybody's ever seen the Intel instruction set, it's quite complex and difficult to get right. So the way we avoided initially was the only piece of code that we had that needed to do memory mapped I/O was the local APIC. So also around that time, Intel had just introduced a new method for accessing the local APIC called X2 APIC, which used MSRs to access the APIC. So you would do a write MSR or a read MSR instruction. And the VTX actually kind of does all the work for you for that. It tells you which MSR was accessed, whether it was a read or a write, what the value was. So you just have to kind of fill in one value and return it. So that meant we didn't have to do any instruction emulation. And by reducing the problem to this, we were actually able to get a modified FreeBSD up and running fairly quickly. In May of 2011, I think during the development of bhyve, we worked out that NetApp as a company didn't really want to be in the hypervisor business. We could keep it internally, but given the limited development resources we have, it seemed like it was only ever going to be just a curiosity. So rather than just keep it internal, we decided to release it to FreeBSD under a 2-clause BSD license, which meant anybody could use it for whatever they wanted. So we were able to get that done in time for BSDCan in 2011. One piece that was missing was at NetApp we actually have a proprietary loader that's based off Broadcom CFE. So we weren't able to release that. So we had a whole lot of code, but we didn't have any way of loading an operating system. So fortunately, by going to BSD conferences, you talk to people that work on different parts of the system. So Doug Rabson, who had done a lot of work on the FreeBSD loader, was at this conference, and he basically knew exactly what we wanted, and over one night he came to us the next day and had most of the loader written, and then we just added a few little pieces, so by the end of the conference we actually filled that gap, and that's where bhyve load came from. The initial development of bhyve was done on 8.2. We actually wanted a stable operating system release to do the work on. We didn't want to try to find bugs and that were being introduced during development of current. However, as soon as we put the code in a project branch, once again overnight somebody went and ported it, or went and synced with what was then current, which was FreeBSD 9. So within 1 week we were already kind of getting the advantages of interacting with the open source community. However, after that, we were kind of pulled off to another project which took most of our time. I basically just tried to keep it synced with FreeBSD because I knew that we would get back to it eventually. It did take about almost a year. However, we were able to do enough work to get it running with current, and we actually merged our project branch into FreeBSD head in January last year. After that, actually, there was a very large amount of activity, especially towards the end of last year, just as the 10.0 freeze was announced. So we then had to try to finalise what features we thought would be important for 10.0 and focus on those. And so it's now actually in the 10.0 release. However, the flurry of activity has continued, so there's a lot of new work that's happening in current. So now the problem we have is trying to pull that work that's in current back into 10.0, which is actually quite time consuming. And it's really the kind of dirty part of development. Nobody wants to do that. So I'll talk a little bit about what's going to come up next for bhyve. So I've just split this into a number of different sections. One of the most interesting ones for us is booting. So currently we actually have a user space loader where the operating system is loaded by a program that runs on the host. So to boot FreeBSD, we have bhyve load, which is a port of the FreeBSD loader code to user space in FreeBSD. The reason that we did that is what I mentioned earlier, that we first did development on the Halem. The Halem didn't have real mode support, so we had the option of either trying to load the operating system quickly with a user space port, or implement BIOS with instruction emulation. We felt that that was going to take probably many months, and we didn't really have that amount of time to do this. So the most expedient way to get things working was just to port what was in our proprietary loader to user space. So the user space loader is really like a legacy feature. It was just a byproduct of how we did development. When it came to booting Linux, of course, because we had a FreeBSD specific loader, we then had to work out what we were going to do there. It turns out that Grub version 2 was actually a very portable piece of code as well. I mean, it runs on a lot of CPU architectures, different endians. It's just generic C code. There's already a user space target for Grub, which is really designed to test or provide a development environment for file system development in Grub. So what Grub bhyve is the Grub mu user space target of Grub, and it's just hijacked and had some bhyve additions. So basically we can boot most operating systems that can be booted by Grub. Now, unfortunately, not all Linux distributions are Grub 2 native. So in particular, CentOS 6, RHEL 6, and even RHEL 7 are still Grub version 1. The syntax isn't the same, so you have to sort of manually translate the menu.list, I think, in Grub version 1 to grub.conf, which is not very pretty. But that just highlights the fact that the user space loader is really not the right approach moving forward. You basically have to have a loader for each guest operating system and target it. And while that works for FreeBSD and maybe Linux, as soon as you go past that, it's just not really scalable. The other issue that we have is having a separate program that loads or has to create the virtual machine and then another one that runs it. There's kind of a gap in the middle where during that time, no one knows who owns the resources. I mean, you can kind of track it to the virtual machine, but our goal is to eventually allow non-root users to run bhyve. So we don't want to allow users just to kind of take up all the memory in the system just by creating virtual machines. But then there's no process that's associated with it. It's just kind of objects in the kernel that are just hanging around on their own. So our goal is to actually be able to have just a process that's associated with the virtual machine. So to do that, we can't have two processes that are involved in the creation and destruction. So our solution for this is to actually go to what's effectively a BIOS. So rather than, there's the other issue with the BIOS is that there's no real BSD licensed BIOS. There's kind of at least one we know, but it can't even be assembled without a proprietary assembler. It's all 16-bit code. And also with bhyve, we don't really want to kind of look backwards. We want to try to have development moving forwards. So what we're planning on doing is actually using Intel UEFI as our essentially boot firmware. There's already a target, a build target in UEFI called OVMF, and that implements essentially a ROM image for QEMU. Now the difference in what they term a ROM image here is when you're running on a hypervisor, you don't have to go and probe all the DRAM chips and work out what's there. You don't have to have knowledge of the actual hardware platform that you're running on. You can query the hypervisor to ask how many CPUs there are, how much memory there is, and maybe some other parameters. So it's slightly different than a ROM that would run on a real hardware platform. Although with UEFI, probably 90% of the code is actually the same as in a real ROM. We had to make some slight modifications to bhyve. It's different than QEMU. In the OVMF target, there's implied devices that exist in QEMU that don't exist in bhyve. So we just conditionally compile that out. The one issue with UEFI is that if you have operating systems that aren't EFI aware, and of course the big example is FreeBSD, you can't actually boot it. So we can boot most recent versions of Linux quite fine, except our main customer can't be booted. So the way we're going to get around that is UEFI has a module called CSM. I think it's a compatibility services module, but it's basically a way to implement BIOS calls in EFI. So I'm sure a lot of you have machines that have EFI and they always have a BIOS mode. So what happens when you do that is it doesn't actually boot the BIOS, it just tells EFI to run the CSM compatibility module, which traps BIOS calls and then vectors it to EFI. So there's all this kind of transition from 16-bit mode to 64-bit mode and backwards and forwards. But basically it's a way that you can implement a BIOS without having to have a BIOS. Now CSM isn't in the Intel EFI distribution. They expect that if you're implementing that, you're going to go and pay Phoenix or someone to give that to you. So we're actually going to implement that and include it in our version of EFI. BSD license too, of course.
Your own CSM?
Yes, so we'll have this up on GitHub somewhere. We'll fork the Intel EDK2 and we'll put CSM in there, which will be BSD licensed. And then that will basically be a binary, and then we just change bhyve so that it will place that in memory, just like a ROM will be located. Once we do that, we'll try to switch bhyve just to a single process model where everything is, when you create and start a bhyve, it will be in the same process that runs it. So all the resources that the hypervisor uses will be associated with that particular process. And then once we do that, then I think we can actually make this accessible via non-root users.
Question on BIOS. Does any of that help or harm CPU abstraction, so you could perhaps suspend a VM on a given machine, wake it up elsewhere, be it UEFI or otherwise?
No, the hypervisor doesn't know that it's running a ROM. It just gets told to start at the real mode start point, just like as a power on condition. From that point on, it has no idea. I mean, you could actually suspend and resume while you're in UEFI. There shouldn't be any issue with that. So just on storage, as Tukiya mentioned, we currently support VirtIO block and AHCI device models. That actually covers 99% of operating systems that we're interested in. Depending on how far back in time people want to get bhyve working, you could actually implement an ATA device model, but I'm not actually going to do that. I prefer to try to look forward. One of the issues we do have is that, currently with emulated I/O, you have a device model, and then you have how you want that device model to access the real world. So for storage, currently we just use a file to emulate a block device. That's perhaps not as flexible as it could be. You may want to, for instance, have an iSCSI initiator. You may want to use some other access protocol. So we'll try to put some more flexibility in that, and that's more of a general thing. In all our device models, we want to have like a pluggable back end, and we really don't have that infrastructure yet. Some of the things that I think we can see doing, we don't have a VirtIO SCSI emulation. That's probably not that hard given we have a lot of VirtIO infrastructure. And what that allows us to do is just support a much larger number of disks. With VirtIO block, you can only support effectively one disk per PCI device, and we're somewhat limited in PCI devices, but it's just unwieldy to sort of have to configure a whole lot of PCI devices. It's much easier just to say I have one SCSI device, and these are the 15 LUNs that are behind it. One area that I think we really do miss out currently is that we don't have any way of accessing disk formats that are created by other hypervisors. So of course a very popular one is VMware's VMDK, and in particular FreeBSD builds actually build a VMDK as part of their output, and also a QCOW2, I think. So the irony is that we can't read the VM images that FreeBSD creates, which is a little silly. So to do that, we sort of need like a filter layer where you can insert one of these modules that will do the translation from like a block number into where that lives on the sparse device. For networking, currently bhyve is very bare bones. We have a VirtIO net emulation, but it only has a single queue. It doesn't even support checksum offload. We did the absolute minimal amount of work that was necessary to allow FreeBSD to see a network. What that means is you don't get any performance. I think we get about 1 gigabit maximum currently. There's two things we're going to do there. One is we'll try to beef up the VirtIO net device model a bit. In particular, something like TSO is very effective with this. The biggest hit with performance of a hypervisor is exits. So what TSO allows you to do is just send more data with less exits. So that's probably one of the first things we'll do. Checksum offload. I don't know if that really makes a whole lot of difference. We'll also try to put in multiple queue support with VirtIO net. It's actually in the standard now, and most Linux distributions support it. That's more multi-processor scalability than just individual connection throughput. So there are still a lot of operating systems that actually don't have VirtIO net emulation, in particular Windows on the install CD. You can get a Windows qualified driver from Red Hat, but then you have to do either reburn your install CD or insert that as you're doing the install. It's really not that pleasant a thing to have to do. So the way we're going to get around that is actually put in some Intel device models. So of course the classic device model is the 2001 era E1000, which also has no real features. It doesn't have TSO or jumbograms. However, every operating system under the sun supports some variant of E1000. It's actually not that hard to do, so we'll try to get that in. A more modern version of that is the 82580, which is Intel's quad port 1 gig, but it actually has multiple queues, TSO, checksum offload. It has a whole lot of modern features. So that will be the performance version of the E1000. I think VMware calls this the E1000E in their configuration. Much like storage, we don't really have a very flexible back-end support for networking. Currently it's only tap device. That's somewhat limiting. So what we'd like to see, we actually have some patches to implement NetApp, courtesy of the University of Pisa. So we're working on trying to get that in. I think that'll certainly give very good performance. It still requires root access. One interesting thing I'm looking at is there's a open source project called WAN Proxy, which is a port of the FreeBSD TCP stack to user space. So the way that I would use that is QEMU has a feature called host-only networking, which basically does NAT in user space and then originates a connection as like from a host process. So it allows you to do networking without requiring any privilege. So rather than kind of bundling all that into bhyve, I have that as an external program which you could talk to with a Unix domain socket, which wouldn't be privileged, and then you could run bhyve non-privileged but still access the outside world. You know, modulo the fact that you couldn't use privileged ports or anything like that. Probably our performance play would be exactly like what QEMU does, and we would have virtio net ring handler inside the kernel, so we wouldn't have to transition to user space and then copy the packet back into the kernel again. We could just handle all the VM exit inside the kernel. So it gives you very low latency, and it should be pretty good for throughput. I mean, my view of the world is really server class systems. You know, we only need console networking and storage. However, the BSD user community, I think, wants to see kind of more like a desktop oriented product where when you start up a hypervisor, you get a screen and you have mouse and keyboard emulation and perhaps sound and other things. The only thing I'm really looking at currently is video, and this is more like for Windows Server installs where it doesn't really work over a serial console. So the kind of lowest common denominator for video for hypervisors is the Cirrus Logic emulation that's in QEMU. So I think if we do that in bhyve, we'll probably cover most operating systems that we care about. The one issue is that, you know, it's one of our main goals is to keep bhyve in the FreeBSD based system. So that means it has to be BSD licensed, and it also can't use components that aren't in the base system. So anytime we want to do graphics, you usually need, you know, some kind of X windows or something that isn't in the base system. So to do video on bhyve, we actually just need some kind of interface that you know, we could load video drivers at runtime. We might be able to put like a small VNC or really dumb VNC stub inside bhyve. But if you want to do anything sophisticated, that's really going to have to come from the ports collection, and then that can't be in the base system. So we just have to provide an interface there. Keyboard, mouse, I don't know. I mean, Takuya did a GSOC project last year for USB emulation. I'm not sure how we can get that in. So far, we just haven't really had the pressing need for it. And of course, an even less pressing need is sound. If somebody actually wanted to implement sound, I'm not going to stop them. There's a number of features that we don't really have in bhyve that some people consider essential in hypervisors. A fairly simple one is suspend and resume. We don't have any way to do that currently. You can actually send the process a stop signal and it will stop, but it doesn't stop very nicely. You can send it a start and it will restart, but when people talk about suspend and resume, they really mean suspend to disk and resume from a saved image. So we can actually save memory fairly easily, but what we can't save currently is device state, meaning a device emulation. You kind of have to record you know, the state of all the registers, the internal state machines, the state of the back end that you're talking to. So we have to have a way to serialize and deserialize that. CPU state is probably not so bad. We already have a way to extract that, but it's for each device, you know, not only is writing it kind of difficult, but being able to you know, save the state and then resume it and start from where you were is actually quite a difficult problem. Live migration just is an exponential increase in difficulty with that problem, because not only do you have to be able to serialize and deserialize, but you have to do it while the system is still running. And you have to be able to do it so that you can move to another machine and give the illusion that the machine was never stopped. So that's probably going to take quite a long time to get right. Another thing that we're looking at is the ability of bhyve to actually run bhyve. So this is kind of known as nested virtualization. So it's being able to run a hypervisor as a guest operating system. The main issue there is that you don't get any support from VTX. All the support that it gives you to run a guest is gone when you run a nested guest. Like the nested paging support, it doesn't have hierarchical nested paging. It can only do it at one level. So then you have to kind of fall back to the previous generation, not doing shadow paging. You have to try to, well, you have to do an emulation of VTX in software, which is actually kind of a large project. We are working on that, but it's just going very slowly.
Is the return there, or is it for debugging bhyve on bhyve?
Yeah, it's, I mean, in the way that hypervisors always they always pitch it as debugging, and it's such a great debugging tool. You know, when VMware first came in, it's like, oh, you know, if you need to test your web browser on all these different versions of Windows, you can just run it on your desktop. I mean, for bhyve, it's like, you know, if I wanted to test FreeBSD, I can just run it on my desktop. I can run different versions. You know, I don't have to go and hook up a machine. So as a hypervisor developer, it's kind of a logical step. It's like, I want to debug the hypervisor, and a lot of hypervisor development is it's not really low-level work. It's, you know, like doing a device emulation. That's really just user space C, stepping through with a debugger. But just like, you know, not doing normal development, you don't want to have to go to the lab and rack up another machine just to do that. It'd be really nice if you could do it on your desktop. So in some respects, we're doing it for our own use, and usually what happens after that is people find other uses for it as well. So currently, bhyve is x86 only. In fact, it's 64-bit. It's x64 only. We didn't do any work at all to support a 32-bit Intel host. It just didn't really seem worth it. The amount of memory available is quite small. However, there's nothing in bhyve that is really inherently x86. The code is mostly generic C. I mean, there's you know, the kernel module certainly has large parts of it that are Intel specific, but they can be separated out without a great deal of difficulty. So that the model itself is quite amenable to run on other architectures. And in fact, I think KVM has shown us, and they have been working on PowerPC and ARM and MIPS too, I think. So there's nothing that would stop bhyve being ported other than just people and time. So with ARM, there's some new models of ARM that actually have pretty much identical hardware assist to what Intel offers with VTX. So for the 32-bit CPUs, the A7 and A15 have the virtualization feature, and of course the 64-bit A54 or 58. It has the same features. So given that it's very easy to get these days, the A15 is a Google Chromebook. That would be an excellent place to start development. For MIPS and PowerPC, not so much. There are some models of PowerPC that sort of have the hardware assist, but PowerPC is kind of slipping off the radar a bit. It's not easily accessible anymore. MIPS, there's a document that's been written on what is basically it's a variant of whatever the latest MIPS 64 is that has the features that are needed, but I don't think that's available in a consumer product yet. So really for bhyve to be useful, you either need someone to sponsor it commercially to development or something, or have a very easily accessible hardware platform. So we don't actually have either of those, so MIPS or PowerPC. But similar to sound, I'm not going to stop anybody that wants to do it. That's pretty much the end of my slides. Did anybody have any questions?
The
The MIPS stuff, do you know if that's in a newer MIPS processor rev, or if it's somebody else's extensions that aren't really part of the MIPS standard yet?
So the new owners of MIPS actually made publicly available a document that wasn't previously publicly available. So I don't know what their roadmap is. I mean, I had a glance over it. It seemed to make a lot of sense. You know, it virtualized the things that you want to see virtualized. But I have no idea if it's in a commercial product.
I've got several questions, actually. Is there any NetBSD support at all for what you're doing?
As a guest or a host?
As a, I would presume as a host. But.
No, so the code is all under a 2-clause BSD license, so you know, Net or OpenBSD are free to take the code and do something, but I haven't seen.
How about as a guest?
So until very recently, NetBSD's VirtIO implementation didn't have MSI support, which was the only interrupt support that bhyve supported. However, in the last 3 weeks, I think 3 weeks ago, we actually put in legacy interrupt support for VirtIO devices. So I haven't tried it for a while, but actually maybe this week I'll spin it up. I just fixed a bug that prevented OpenBSD 5.5 from booting, but that now seems good again. So I think that BSD might be okay.
Would it work maybe with the HCI instead of VirtIO with this?
No, because I don't think they have MSI. So actually, AHCI we still require MSI support. We don't have legacy support.
So another question is, in the QEMU world, there's a lot of options now for a lot of different kinds of device support. Are you headed in a similar direction, or is this going to be in your? Will you be bundling this stuff into bhyve proper, or will it all be optional command line parameters for including different devices? What's kind of the direction where you're thinking of going with that?
The opposite of QEMU, I think. So my issue with QEMU is it's just a huge piece of code. I think there's like 1 million lines of code in that piece of software. It's they have a very large community working on it, but also I think their rate of development is really slowing down just because of the size of it. And also I think with such a large piece of code, you can kind of have a lot of security issues. I mean, anything that you get with just a big piece of code. With bhyve, we've always wanted to keep it as minimal as possible. For device models, so one of the issues I mentioned earlier is just video. We can't really include a lot of video things in bhyve just because it's not in the base system. So we have to make that kind of modular, and we have a way at runtime that we can load backends. I think for device models it will be the same. You could write a device model that would be external to bhyve, and it could potentially be in the FreeBSD ports collection, and then we can just load it at runtime.
Should be like a kernel module, a bhyve module, for example.
Yeah, this would all be user space. And so if you wanted to write a LAN's Ethernet device emulation, we probably wouldn't put that in the base system. There's not a lot of use for it, but if we have a loadable module framework, that could easily be written externally and just pulled in at runtime.
So there's another component that QEMU has incorporated is the SDL, low-level device support, or support for various devices through SDL. Is that the kind of thing that could be done here in terms of incorporating easily for video and all that? Or is that?
Yeah, so SDL, once again, it's not in the FreeBSD based system, but I think it's a fine target for a backend. So the way that we would handle that is you would have like a loadable module that would link against all the requisite SDL libraries, and then that would be pulled in at runtime. So we wouldn't have to have any knowledge of that in the base system.
Thank you.
Any other questions? All right, thanks very much.
Oh, yeah. Yeah, if it's new, it's from